thousands of microscopic particles, 200 times the mass of an electron, bombarding our world, going undetected. However, in this lab, we shall detect and measure the characteristics of these particles known as muons.
For this experiment, we looked at different properties of muons, which are subatomic particles very similar to electrons, but with a much greater mass, about 207 times more. Muons are formed when cosmic rays collide with Earth's upper atmosphere, about 10 kilometers up. These cosmic rays contain protons and various other elements, and they decay into pions, neutrinos, and muons with either a positive or a negative charge. Some of these pions eventually decay into even more muons, which also have either a negative or positive charge. These muons will eventually decay into either an electron or a positron, depending on the charge of the muon, and two accompanying neutrinos. Muons are very unstable particles and have very short half-lives. Our experiment had two primary goals. The first was to measure the flux rates of muons at both 12,740 feet up at Pikes Peak and at 6,040 feet here on Colorado College's campus. We hope to explain the difference in these fluxes. Our second goal was to calculate the half-life of a muon. Our hypothesis for the experiment was that the flux rates would be higher up on Pikes Peak and lower at Colorado College's campus, considering the fact that muons would have less time to decay by the time they reached Pikes Peak at an elevation of 12,740 feet. Once we started the experiment, we realized that to calculate the half-life, we would have to include time dilation. Since muons are formed in the upper atmosphere at about 10 kilometers, they should not even exist as we see them, whether on Colorado College's campus at 6,040 feet or at Pikes Peak at 12,740 feet. They shouldn't exist anywhere on Earth's surface, according to how we see them, based on their short and unstable half-lives. But we realized that due to their high speed to the relationship of the speed of light, muons would undergo time dilation from their own reference frames, so we knew we had to take this into account when looking over our data.
In this experiment, we used a device called Muon Physics by TeachSpin. This device is composed of a plastic scintillator, a photomultiplier tube, and a signal amplifier. This device measures the time between light pulses, and this gives us the raw data that accounts for the muon's lifetime. This device measures this, in the case of a muon, by measuring two different things, either a muon passing through the detector or a muon decaying inside the detector. In the case that the muon passes through, it imparts some of its energy and it excites particles inside the scintillator. So we would see a flash of light in here, but this flash is not able to be detected. So what happens is this energy is transferred into the signal amplifier, and this light flash corresponds to that. There is a slight time delay in between the flash inside the scintillator and the flash from the signal amplifier. This time does not matter in our data though, as both of these values end up having the slight time difference, so we can disregard it. In the case of a muon that decays inside the detector, it is actually with a positive muon and then a negative muon. A positive muon is made up of a neutrino, an antineutrino, and a positron. And a negative muon is made up of a neutrino, an antineutrino, and an electron. It is the same case with the muon that actually passed through. The electron and the positron excite particles inside the scintillator, which then sends that pulse to the signal amplifier. We began the experiment by measuring the flux and the half-life at Colorado College at an elevation of 6,000 feet. We did this by filming the light flashes and listening to the clicks from the audio. We also then took this device up to an elevation of 12,000 feet on Pikes Peak. We again repeated this experiment and were able to attain a flux at the different elevations. We also, at CC Base Camp, analyzed the data that the computer collected and were able to determine what the half-life was from that data. As we know, half-life is not dependent on elevation or altitude and is constant, so we did not need to measure the half-life at Pikes Peak. We were just able to do it at Colorado College.
Using the audio feature on the muon detector, we were able to calculate every time that a muon was detected using the clicks produced. Slowing this down and thus looking at the sound peaks, we were able to split up a 1 minute segment of audio into different 1-second segments in order to calculate the amount of muons detected per second at each elevation, as shown by the video here. Each peak corresponds to a muon being detected, and thus allows us to calculate the average amount of muons detected at each elevation. The muon detector, we are able to calculate the half-life based on the muons coming into the detector, stopping, and thus decaying. Over a 16-hour period, only 257 counts were measured. These counts corresponded to muons actually stopping and decaying within the detector. To my right here, we sorted the data and were able to eliminate the simple frequency of muons passing through and only get ones that decayed within the actual detector. These different values were then averaged, and we found an average decay rate of 1.33 microseconds. This graph here shows the muons that exist based on their lifetime. At the upper leftmost corner, you have muons with a short lifetime. Therefore, every muon existing has a greater mean lifetime. As you move further to the right on the x-axis, the lifetime increases and thus the existing muons decreases. This illustration is similar to the problem when it comes to flipping tails and heads, while we keep tails and disregard the heads that are in the experiment. As you can see, the left axis is utilizing a logarithmic scale. If this were perfect data, we would theoretically get a straight line coming from our upper left point to the lower right point. However, this data is not perfect and has its own uncertainties involved. Using the previous illustrated audio techniques, we were able to measure the flux at each elevation, those being 6,040 feet and 12,740 feet. To my right here, that data is collected, and in that 60-second time interval, we split the audio clip into 1 second and counted how many muons passed through during that 1 second. This graph then shows that data as we have the muons detected on the y-axis and the seconds passing through that full minute. This linear bar here shows the average amount of muons detected per 1 second, that value being 1.55 muons per second at the elevation of 6,000. The muon flux for the higher elevation on top of Pikes Peak at 12,740 feet was calculated the same way as the previous lower elevation flux. Once again, we slowed down the audio frame and we're able to count the amount of muons detected in each second. The graph here illustrates that as well, and then once again the linear bar shows that we had an average muon detection of 3.55 muons per second. Combining these two pictures gives us this graph here, and we can clearly see that the blue is the higher elevation of 12,740, and down here in the orange we are on campus at 6,040 feet. You can see that the blue remains almost entirely above the orange throughout the 60-second interval, and the linear graph bar shows that it is almost a difference of 2 muons per second. This flux will then later be explained by time dilation, as the muons are required to travel that distance without decaying. As stated in our previous analysis and data collection, we calculated that the decay time for muons once inside the scintillator to be approximately 1.33 microseconds. Now this value happens to be the mean lifetime rather than the true half-life of muons. The relationship between these two values happens to be quite simple. As shown here, the half-life is calculated to be 1.33 microseconds, or 10 to the negative 6 seconds. The equation to get the half-life from mean lifetime is as follows, where t1/2 equals the mean lifetime times the natural log of 2. Although we continue to use the mean lifetime as our half-life in later calculations, we went back to find what exactly the uncertainty in this would be, and in fact the order of magnitude does not change. Using this equation, we can calculate that the actual half-life of muons is around 1 times 10 to the negative 6. The difference between these numbers may seem significant, as it is a difference between 1.33 and 1. However, though, the magnitude does not change. Therefore, 10 to the negative 6, anything, is going to be very similar and thus give us accurate results continued through our experiment. This is just one example of the many uncertainties and approximations that went into this calculation and ultimately the lab of muons. Using the data calculated from the muon detectors program, we were able to discover that the half-life, in our case, was 1.33 microseconds. Theoretically speaking, muons would not exist at any elevation below our atmosphere because of that very, very small half-life. Because of this, we must look at this picture here and understand that muons are created approximately 10 kilometers up in the atmosphere. With such a small half-life, all of the muons, no matter how many were created to begin with, would never make it down to the elevation of even the top of Pikes Peak. This problem led us to understand that special relativity must be taken into effect. As we have previously learned, there are two consequences of this, and those are follows as moving clocks run slower and moving objects are shorter in the direction of motion, both by a factor of gamma, which we will later calculate. From this, we can understand that muons are actually experiencing a shorter distance in their reference frame. So instead of traveling 10 kilometers, they're traveling 10 kilometers divided by a factor of gamma.
Okay, so from Brian's data analysis, we know several important data and numbers. So we know the flux that we measure on the campus, which is 1.55. We also know the flux that we measure on the mountain, which is 3.63. And we also know the half-life of the muon. And the half-life of the muon is 1.33 microseconds. So, in order to do the following calculation, we need to first know how much time that the muon actually travel. So we need to introduce a whole new calculation formula. Let me write it down. So we can see here in this formula, negative t, here we can see that it actually show how much time the muon actually travel. So, and also this individual symbols also correspond to the numbers, actual number, right? So we can use this equation to determine the t. So let's do the following calculation. So if we reorganize this whole formula, we can determine t. And the t here is 1.59 microseconds. So according to the time we calculate for the muon, we can actually calculate the speed that muon travel. Let us do that. So we know the distance from the campus to the mountain, which is 2042 meters, and we also know the time for muon's travel, which is 1.59 microseconds. And then we can calculate that the speed of the muon is 1.28 times 10 to the 9 meters per second. But here comes the question. According to relativity, theoretically, this particle cannot exceed the speed of light, which is 3 times 10 to the 8 meters per second. So even though we do all of the calculation right, we can still get a wrong answer. That's only because we have miscalculated the distance from the campus to the mountain. Okay, so I was just talking about the distance that we miscalculate. The reason why we miscalculate that is because we forget to let time dilation and relativity to involve in this situation. So in order to let the audience understand it more, we can draw a graph to explain it. So here we have the mountain. So let's just say that we measure the flux over the top of the mountain, and also here, this is where the campus located. And for the observers like us, we are standing on the Earth. This is us, and we have our own clock. But for muon, let's first we need to know that the muon travel is similar to the light. So the speed between those two are similar. So for muon, it has its own clock due to the different speed. So let's calculate those two different time individually. So as I just said, the muon travel just like the light, so their speed are similar. So that's just assuming that approximately the speed of muon is the speed of light, which is 3 times 10 to the 8 meter per second. And we also know the distance between the campus and the mountain, which is 2042 meters. So for our point of view, for our observer point of view, the actual time for muon to travel is the distance divided by the speed of muon. And we do a little calculation. We can see the result is 6.81 microseconds. But here, when we analyze what muon found, the situation is totally different. And we already calculate that the t, just like I showed you before in the last graph, is 1.59 microseconds. So we just mentioned about relativity. So there are two things we can derive from the relativity. The first one is for object that travels similar to the speed of light, the distance is shorter, and its time that they actually experience is lower. So we can see that this 2t, we already calculate that. If we determine the gamma, we can know the speed of the muon that it actually has. So let's just reorganize this calculation, this equation, and we can get muon, which is 4.3. Okay, so that's the factor we need. So originally, if we want to calculate gamma, we can use this equation. So here in this equation, we know the gamma is 4.3, and we also know the speed of light, so we can determine what's the real speed for muon. We organize this, and we can get the speed for muon is 0.97 times the c, which is the speed of light. So we can see here that if the muon travel in this speed, time dilation definitely evolve into this situation. So that's why, even though the decay time is so small, we can still detect the muon that is not decayed on campus.
In culminating this lab report, we have successfully accomplished our 2 goals for the muon experimentation. The first of those being to calculate the decay time or half-life of a muon. As previously explained, we calculated the decay time to be 1.33 microseconds. Now this is not the exact half-life, but rather is related to the half-life by multiplying by the natural log of 2. However, we are able to disregard this information since microseconds is actually a magnitude of 10 to the negative 6. So, we can finalize that the decay time or half-life of a muon at any elevation is approximately 1 times 10 to the negative 6 seconds. This being our first goal. The second goal of the experiment was to differentiate the flux at an elevation above 11,000 feet and an elevation at CC's campus, being around 6,000 feet. For this, we traveled to the top of Pikes Peak and reached an elevation of 12,740 feet for our upper elevation experimentation. With this differentiate, we found that the flux at the high elevation, flux at above 12,000 to be 3.63 muons per second being detected within our machine, and then at the lower elevation to be 1.55 muons per second. As we explained, this is only possible, this differentiate and flux is only possible through Einstein's special relativity, because the time that it would take even a particle moving at the speed of light to travel a true distance in our inertial reference frame of 6,000 vertical feet, or around 2,000 meters, is much, much larger than this 1 times 10 to the negative 6 seconds. So, through time dilation, we are able to understand that the flux is completely reliant on a shortening of distance through that second postulate of Einstein, and that moving clocks run slower and distances will be shorter. Thank you for watching once again, and we hope that you learned a little bit on muons and hopefully got a taste of special relativity.
At the beginning of this experiment, we were unsure about what to expect, as muons were a foreign concept to us.
Through this lab, we're able to use new forms of data collection, and we're also able to apply special relativity and time dilation in a way we haven't seen yet.
Ultimately, we gained a greater understanding and appreciation for the physics behind muons and their creation. Through measuring the difference in flux at an elevation on top of Pikes Peak as well as on campus, we are able to apply the theory of special relativity and thus explain why muons are found at this lower elevation. Additionally, the half-life was measured, and we were able to constitute why this half-life does not change, and in fact muons are decaying as they come down, yet are still found at the low elevation.
Okay, so this is the conclusion of our lab report. Thank you so much for watching. If you have any question, please feel free to email us. Thank you so much.